Yeah, so at x equals 4, we're trying to determine, is this problem continuous or not? At 4, here's x equals 4. I can help you out. Let me type in x equals 4 so it draws your attention. At 4, is this graph in one piece or is it broken apart? It's broken apart. Good. If you remember from last class, there are 4 types of breaks. It could be an infinite discontinuity, it could be a jump, or a removable. Which of those 3, infinite, jump, or removable, would define this break? Infinite, because the limits at the break would be going to infinities. So in terms of limits, so I write this answer from the top. In terms of limits, an infinite discontinuity is when the limits are going to infinities at the breaks. A jump discontinuity is where at the break, the limits are going to 2 different numerical values. A removable discontinuity is at the break, the limits are approaching the same number from both sides. So in those random examples, I gave you some of each of the 3. All right, and now let's check number 3. Number 3 says determine whether this function is continuous at x equals 2. So I'm coming over here and I want to look at the number 3. So I'm going to close off bell ringer number 2. Now number 3, I'm going to click this. I want you to tell me, what do you think about the number 3's graph? Does that appear to you? This is a piecewise equation, by the way. That's what piecewise looks like. This is going to be multiple pieces of graph. It's going to be 2 different pieces of graph. So you can see here. But do those 2 pieces, are they continuous, making one graph, or do they stay separate? Okay, well, by appearance, do they look separate or they look together? They look together. Here's how you test, is you need to check the value at 2. That's where the one piece that is a line will run into the piece that's a parabola. And so at 2, you need to see, is that a real number or will it say undefined? And you might have to zoom in. So I zoom in, there it is, 2. Is that a closed dot or open dot? Is that closed? Does that mean it's continuous or discontinuous there? Continuous. So f of x would be continuous. F of x is continuous at x equals 2. And I need to show you on, if you need to graph piecewise for any of your homework or anything like that, if you click on the Desmos pre-programmed graphs, it is the second link. The very top link is insolve. If you remember insolve on the Inspires. The second link is how you can graph piecewise. If you open that up, there is instructions you can follow through and it'll graph it for you. So in this particular problem, I would just say, okay, the first graph was that x plus 6. I'll get you in a second. X plus 6, where x is greater than or equal to 2. So there would be the first piece. And the second piece of graph was that x squared plus 4 when x is less than 2. And it would it'd show you the graph just like that. It would put it all together for you. All right, we have a question. All right. Oh, over here on Desmos, there are a couple of extra examples I can show you that'll just kind of go over some, let me get here, some different graphing things. So I want to show you some different limits that we might see. I need to go a lot higher, I think. Is that what it was? And -10, +10. Not seeing the pieces yet. I can't remember which way I need to zoom out. Hang on one second. Well, there's another piece of graph. There it is. There, I found it. Sorry. We will go over a couple extra examples. Okay, I want you to take a look at this problem here. If you had to describe the end behavior, what's happening as this graph goes forever to the left? How would you describe this answer? It would be going left or downward to -infinity. And what happens to the end behavior as this goes right? Positive. Okay, different question. I'm going to flip the limit around. what if I told you, so this is not the way we usually write it, but I'm just going to see if you understand. It might help you to kind of go backwards. What if I said we want the piece that's going up forever that's right here? What X value, I'll tell you the number 7. What would go with the 7 to describe this piece as opposed to this piece of the break? Plus. That plus means right side. Okay, and so on the opposite end, if you wanted to talk about this piece that's going downward forever, and the break is at 7, what would refer to this piece that's on the left? A minus, you would need that. And so those would be the 2 inside limits there. All right, on the next graph here below it, if I clicked on this one, I'm going to zoom in. I want you to look at this graph. If I were describing the end behavior on this graph, I would, on the end behavior, I'm talking about going left and right. What is happening this time as you go to the left? Let's start there. Would this be one of those limits that the graph is increasing forever as you go left? Would it be one of those that's decreasing forever as you go left? Would it be one of those that's getting really, really flat as you go left, or one that's stopping at a point? What's happening to this graph as we go left? It's getting really, really flat. And if you click on it and you see this graph is approaching the number, now remember, it never actually gets there. What Y value is it getting really, really close to? 0. Nope, the Y value. It's getting really close to 6. So the correct answer for this limit would be 6. And you can do the same thing as you go right. This one's also really approaching. You see how the Y value is getting close to 6? As X increases, the Y value is getting closer and closer to 6. And you could zoom way out. And at some point in time, Desmos will quit rounding, or it'll just round it off and just say it's actually 6. As you can see, it's really close. I hadn't done it yet. This side it has. Yeah, out here it has. So that was zooming way out. You can see that. So I wanted to show you that problem. And a lot of students ask, what does it look like if it stops at a point? That's what this graph is right there. You see this time, what's happening on the far left? Is it increasing forever, decreasing forever, getting flat forever, or is it stopping at some point? That's stopping at some point. That's what that would look like. Okay, so I just wanted you to see that for extra examples for that problem. What about here? Okay, so for number 3, when we were talking about number 3, I mentioned that if you zoom in, you could tell if it was defined or not. You see how this one now is undefined there, open circle? I can't get it. There it is, undefined. That would be a infinite break, a jump break, or a removable break. That would be removable if you had that situation. And finally, what would you call this break? That would be a jump. All right. So with that, I'm done with those extra examples. Let's do the packet. We're starting lesson 1.4. So remaining in class, we're going to go over packet 1.4. And I'm going to go a little bit quicker because in my experience, many students know what increasing means. What does increasing mean? Going up. And specifically, if we say increasing and it's not a limit, we're talking about it goes up from left to right. Goes up from left to right. So unless we're talking about a limit and we use the word increasing, that's the only time it might be different. Otherwise, we're talking about going up from left to the right. Decreasing would go down from left to right, constant meaning flat. We're going to get to maximum and minimums, which would be the highest and the lowest points. Okay, and we'll finish with average rate of change or a secant line. So with that, here's some diagrams. Increasing means it goes up from left to right. Decreasing down from left to right. Constant would be a flat line in there. First problem. What's this graph doing? Increasing, decreasing, constant. Trick question. It's doing more than one of those things. It's doing 2 of them. It's increasing and it is decreasing. You always list this by X value. So here's what I'm going to show you. The left side. What's the graph doing from left to right on the left side? Decreasing. What's it doing on the right side? Increasing. Let me tell you what students do wrong all the time. Is they'll look at the Y value and say, okay, that point right there is at -4. And they will say, here's what they do incorrect, is they'll say it decreases or it's decreasing from -infinity to -4. And notice what I just did there. I took a domain X value that is left forever, and I took it to the range Y value. You see how that's incorrect? That would be an X and a Y. That is not correct. What you would do is you would take this point and say, well, that's 0, -4. It decreases to 0. And I kind of skipped over this. Let me go back to it on the problem here. Whenever it says to find an interval, intervals are always X values. Intervals are X values with parentheses. You don't use brackets with intervals. So we're just always going to use the X values and we'll put them in parentheses. So this one decreases from -infinity to 0. Again, you're only going off the X-axis values. So it's kind of like similar to domain. But again, no brackets. And this is increasing. Earlier we said it decreased on the left half, increased on the right half. So what X value does it start increasing at? 0. And it increases for how long? Always to positive infinity. So that would be our answer for the first. All right. Part B. I'm going to look at this problem and identify that it's decreasing up until this point here. It decreases to that point, and then it increases, and then decreases again on here. So I want you to see this one. Whoops, what happened? Let me try it again. Red. There we go. All right, what's happening in the first portion? Decreasing. So it's decreasing. It's decreasing from how far left? -infinity. Until, and I'm going to label this point. This point, it seems to me it's about half a unit to the left and maybe about half a unit down. So let's say it's -1, -1. So again, though these numbers are the same, it really helps because we can't get it wrong. Technically, you would go off the X value. So I'd say -1/2 there. Now, what happens in between these two red dots? It increases. So we'd say it increases, or it's increasing, either one. Increasing from -1/2. And now let's figure out where is that value. I would say that's right 1/2, up 1/2 maybe. And so it's increasing now to positive 1/2. Again, you'd be going off the domain values on both of these two. Now, what's the very end of the graph doing? Decreasing. Whenever you have another decrease, you use a union. So it says that's a union means like, it's kind of like or. So it's decreasing here or there, the idea. So from the X value, it'd be 1/2. And how long does it continue to decrease? Okay, now here's what a lot of students will do wrong. Tell me, why do you think some students will all of a sudden put a -infinity there? Because they see it's going down. The word decreasing is telling you it's going down. You need to use the X value. Is this X value going to -infinity?
No.
No, it's going to positive. And so that would be the solution there. So that's how students, that's a common misconception, is that you mix domain and range. It should be domain values. Yeah, it should have been on your packet, right?
No. There's another one that's like opposite of it, but it's not the same one.
Yeah, this is the bottom of the first slide, first page, bottom right. First page, bottom right. All right, now we're at second page, top left. Your first one, DOL number 1. I'll give you a chance to work on this. This point is not very straight. I'm going to put the point right here for you. I want you to use this point there. -1, -2. I want you to use that point. DOL number 1. All right, now I'm going to move into what's called extrema. Extrema refer to maximums and minimums. So extrema, I don't know why I keep wanting to draw that dotted line for me. Here we go. Extrema are terms that means the maximums and minimums. So you have maximums and you have minimums on many graphs. Combined, they are extrema. Extrema just means they're either a maximum or a minimum. Doesn't matter the type. Now you will see that there are relative and absolute. Where's absolute? There it is. Absolute. So the word relative means that it's a maximum, but it's not the highest maximum on the graph. And absolute means it is absolutely the highest maximum. Now, what generates a maximum is when you switch directions from increasing to decreasing. You will have a maximum. It looks like the top of a hill, kind of like here. If you're increasing and then you change directions, it creates a maximum. So this maximum right here is what we would call a relative maximum. You can also call it local. This lesson refers to them as relative, so I'll call it a relative. This would be a relative maximum, and I'm just going to say relative max. As opposed to this one, this maximum would be called a absolute maximum. The difference is the absolute max is higher than the relative. So again, anytime you have a change of direction from increasing to decreasing, you get a maximum. Now I have a question. I bet you can figure this out pretty quick. This one's not labeled. What do you think they would call this point right there? I hear minimum. Let me make it easier for us because some of us are a little tied up because of the picture. What if I made it look like this? What is it now? So I lied. I said I'm gonna make it easier for you. I did not. I actually tried to make it more tricky. This is a relative minimum. Now it's relative because it will that be the lowest point on the graph. Now, so even if this arrow was up higher, the arrow means it continues on and it goes lower. So this would not be absolute. It would be relative. Okay, what about this second graph? What would you call this point right here? Very good. That is a relative minimum. Yeah, minimum. Come on, right. Minimum, there it goes. And finally, this one, what would you call that point right there? That one's an absolute. There's one that's not labeled. What would you call this point right there? This would be a relative maximum. Good. All right. Now with that, let's go through these next few problems. Here, you have two extrema, and you also have what's called a point of inflection. So I'm going to go kind of more proper definitions here. This point is a relative or absolute? Relative. That's a relative minimum because you're changing from decreasing to increasing. So we would have a relative minimum. And a lot of times you list this by x values. The x value would be, let's see, this is counting by twos. This is a little tricky here. It looks like it's counting by twos. So what's in between 0 and -2? -1. I want to say that x equals -1. Now they also might list it as a point, which then you would list it as -1, -8. You could say it's a relative minimum at -1, -8. Do it that way. And there's a second extrema here at this point. And I'm just going to assume that it's on this second line or the first line here, which would be an x value of 2, because again, it's counting by twos. So we would have what was this one, a relative or absolute? Again, relative, which you could also call it local, by the way. A relative maximum at, again, if you label just by x values, you'd say at x equals 2, or you could use the point 2, let's see here. The y-axis seems to be counting by 4s. What's in between 12 and 16? 14. You can list it this way, or in function notation, f of 2 equals 14. You could say that's a relative max. Okay, so now what a lot of students are asking about was, what about around the origin, this little thing right in there? What is that? Well, it's increasing and it continuously increases. It's always increasing. It's increasing faster here, then slower, then faster again, but it's always increasing. So we would not say that's a maximum or a minimum because it never changes direction, but you would call that a point of inflection. So that right in there, that's what they would call that, is a point of inflection. Point of inflection. That's what that would be. Okay, so that brings us to DOL number 2. I want you to take a look at that graph and see what you can come up with on your multiple choice. All right, let's take a look at example 3. Now we're going to use a little technology. So we should all have Desmos open already from earlier this lesson. It gets to guided practice number 3, and guided practice is actually your next slide. I have that typed in for you, but I do not have this example, so I'm going to type this one in from scratch. So I have f of x equals x to the 4th power minus 5x squared minus 2x plus 4. And I'm going to show you something a little bit neat. You might have remembered me saying earlier this school year that the highest power, which in this case is 4, will tell you how many different solutions you could possibly have. Solutions are x-intercepts. The most this graph could ever cross the x-axis is 4 times. Obviously, this is shifted a little bit too high. If it was denoted the plus 4, we would have 4 separate answers. But this one does have plus 4. So I have 2 solutions in that regard. But when we talk about extrema, it's always 1 less than the maximum power. So my maximum power is 4 here. That means at most it'll change direction 3 times. And so when you look at this graph, does it actually change direction 3 times? Yes, it changes direction once here, a second time here, and a third time right there. So the most it can ever change directions is always 1 less than the power. Just wanted to let y'all know that. So since the highest power is a 4, it could change directions potentially 3 times, which it does change all 3 times. So here, what's the other thing I want to point out is it tells you to round to the nearest hundredth. And so the way I think about this is if you're rounding, just because I know some students know this, but others don't. If you're rounding to hundredth, a way I think of it is the number 100 has 2 zeros. Since it has 2 zeros, that means for rounding to the nearest hundredth, you round to 2 decimals. That's how I think of this. So we need to list off our relative minimums and maximums here. This first point, is it a relative or absolute? Relative, maximum or minimum? Minimum. So we have a relative minimum. And it says approximate to the nearest hundredth, the x value, sorry, the x value. So that's all I'm going to write down is the x value. So I have a relative minimum at negative 1.47. I don't have to round that. Desmos has it right there for me. So that one's good. The next one, however, what would you call this point? Relative or absolute, maximum or minimum? Relative. And it is a maximum. Now this one, we need to round. And so as students always tell me, you learned growing up in DIST anyways, that if it's 4 lower, how's the riddle go? Or not the riddle, the rhyme. 4 or lower. 4 or less. 4 or less, let it rest. Thank you. 4 or less, let it rest. 5 or more. How's it go? Y'all tell me. 5 or more, raise the score. 4 or less, let it rest. Okay, that was way too hard for me. If the number is less than 5, it stays. If it's greater than or equal to 5, it increases. So this one, you just cut the 3 and say it'd be x equals negative 0.20. And then finally, the last one, what would this one be right here? Relative or absolute? we'd have an absolute, minimum or maximum? Minimum at x equals, so I have a 0.3 in the end. I need not a 0.3, a 0.673. What do I need to do with that 3? Does it round down or round up? Down, so it'd be 1.67. And that would be our solutions to example 3. So I want you now to try your problem, which I already have this graph for you. If you're on my Desmos, you can just open up the next one, or just turn on the graph, I should say, to find these solutions. DOL number 3. So example 4 now, let's talk about how we use this in real world. So a lot of real world situations, what we do when we talk about Extrema is optimization. So optimization is like the best possible scenario. In this particular problem, it says advertisements for a new car claim that a tank of gas will take a driver and 3 passengers about 360 miles. So you fill up your car with gas, you can drive for about 360 miles before you run out of gas. That's the claim. After researching on the internet, you find the function for miles per tank of gas for the car is given here, where x is the speed in miles per hour. What speed optimizes the distance the car can travel on a tank of gas, and how far can that car travel at that maximum speed? So what I'm going to do here is I'm just going to have a new blank graph, and we'll type in this, see what the equation looks like. Negative 0.025 x squared plus 3.5x plus 240. And now I need to zoom out a little bit. And so when I look, this is a real world problem. So I want to remind you of a term that if I said relative domain in the relative range, what I'm talking about is real world. Question: if x is speed, can you drive a negative miles per hour? No. So honestly, I should be looking at x values that are only have x values that are greater than or equal to 0. And honestly, you can't drive 0 miles an hour. So I'm only looking at this portion of the graph. And not only that, if it's real world, can my car travel negative distance before it runs out of gas? No. So my y's should also be positive as well. So what I'm doing here is adding restrictions. You use these little squigglies to do that in Desmos. And so honestly, that's what my graph should look like. Y is not working. Why is it not working? Can we erase f of x? There you go. And so this is the only portion of the graph you'd be looking at. So the optimized value, the optimum value, it would be the extrema, that point right there. And so that would be my answer on this problem. It would be that point. Now let's talk about what does this mean in the real world. 70 is the x-axis. What was our x value again? Speed. So the optimum speed, or I should say the optimum distance, of how many miles can you go? What is the optimum distance? 362.5 miles occurs when traveling 70 miles per hour. That's the answer on this one. Okay, so I did include the x and the y just to kind of say, because there's 2 questions there. What speed? Well, the speed is 70 miles per hour. And how far will it travel? 362.5 miles. So I included both of them in. That's how you could do one of those problems. So one more time, why on the real world do I cut out the negatives? That's right. Okay, and now I'm going to do this next DOL with you, and I need to go get a box and hang on one second. All right, DOL number 4 says that we have a square with side length x cut out of this rectangle. So actually we have 4 squares, length x all the way around, cut out of a rectangle with dimensions 8 by 12. The figure is folded to form an open box. So here's the idea. We're going to fold along the cuts like this, and we're going to create an open box. So use a little spatial reasoning here. Determine the length and the width of the box to allow for the maximum volume. So when I fold these, my length will no longer be 12 in length. As you can see, this blue line is 12 inches. But we cut out a length of X here and a length of X over here. And so this inside portion, how long is it now after I've cut out all of this and it no longer exists? When that is cut out, how long is this side? 12 minus 2x. And I'm going to call that L. Now let's look at the width. The width originally was 8. But I've cut out this corner and I've cut out this corner and this corner. Those corners are gone. So it's no longer 8 in length. I cut out a length of 8, or excuse me, a length of X, and I cut out a length of X. So how long is my width now? 8 minus 2x, very good. And finally, I have a height that's basically this wall here. How tall is that height? X. Okay, so this problem is asking about volume. You may remember the volume is length times width times height. So if I substitute in, my length is 12 minus 2x. My width is 8 minus 2x. And my height is x. We could graph this to come up with a solution. Now I want to point out, x refers to the height or the amount getting cut out. You could call x the amount getting cut out, or you could call x the height. V is our volume. So when I graph this, I'm going to say V equals, that's going to put the volume in the place of y. Because it's usually y equals, the volume is going to be in the place of y. The x, which is the height or the amount of cut, will be their independent value. So here's our graph. And I want you to think in terms of real world. This is a real world problem. Is it possible to have negative volume? No. So first off, and is it possible to cut a negative part of the box out? I can cut negative inches of box? No. So I'm going to limit my graph. I can only cut a positive amount of the box. I cannot, and I can't cut 0 either. I got to cut something, but I can only cut a positive amount. So I cut off the negative part of the x's. Now, not only is that true, but my volume has got to be positive. You can't have negative volume. That's ridiculous. Oh, and I shouldn't say y. I should say v for volume. It's got to be greater than or equal to 0. And for some reason, it's not working. So let me change this to a y. There we go. And I'm going to come back over here and say y has got to be greater than 0 because you got to have positive volume. And you notice this cut out a lot of my graph. Now, the problem is there can't be this gap. So honestly, after this gap, this part of the problem is bogus as well. So I'm really just looking at this part of the graph. So this is the optimum amount to cut. Remember, x is how much you cut. That's the optimum amount of cut to get your greatest volume. So that's what I'm looking at right there, that portion right there. Now, what's tricky is that looks like it's one of the answers. But I want you to read the problem and identify why that is not the correct answer for the problem, though that's the point that the calculator shows. It is the point, but it's not the correct answer. Why?
Because it says determine the length and width of the box that will allow the maximum volume.
So it says determine the length and width. Is that the length and the width? No. What is this again? That could be considered the amount you cut, or you can consider that the height. So x is the height. And they didn't ask us what's the height. They asked what's the length and width. So how could I get my answer if x is the height and that's what I know? That's right. We just substitute in here. So we could say the length will equal 12 minus 2 times 1.569. And then the width would equal 8 minus 2 times 1.569. I'm going to stop there and I'll let you do the rest. As a reminder, the reason I did not look at, when I looked at this graph, let me go back to the home screen. You cannot cut a negative amount of the box out, so the x's could not be negative. And I can't have a negative volume, which means this problem is no longer realistic after this point. If you're wondering, why is it not realistic after here? Well, you're saying cut more than 6 inches. At this point, you're cutting 6 inches. This is saying cut more than 6 inches. Well, that's just not realistic. If you cut more than 6 inches from this side and more than 6 inches from this side, this whole piece falls off. Same is true here. If you cut more than 6 inches from the left, more than 6 inches from the right, it falls off. So this part is not realistic. You're only looking in this first part that's in quadrant 1. That's all you would use for the real world. With that, let's go to example 5, secant lines. So we have a curve, and on this curve, the values are changing. The slope is changing. You don't have a consistent slope because it's a curve. The slopes are changing. So we have what we call an average rate of change, which means we'll pick 2 points and just say, what would be the average slope between these 2 points? And which ultimately we call a secant line. A secant line is the name for this. There is a formula given here. I will give it in algebra 1 form. In algebra 1, you learned that the formula for slope is y2 minus y1 divided by x2 minus x1. That's your formula that we'll be using to find the slope of this secant line. M is always a letter for slope. So M secant is the slope of the secant line. That'd be the slope of the secant line. That's what that refers to. All right, so now what we're going to do is find that average slope. So you have some curve. You want to find what's it, the average slope, what's it on average doing? And you would use this formula. So here's our problem. And if you look, here's the picture. The blue is the graph of f of x. We want to know what's the average rate of change between on the interval from -3 to -1. So basically from this place, -3 to -1, how much on average is this increasing? And so the formula I just gave you, the formula for the secant line in algebra 1 form was to take the second y, subtract the first y, take the second x, subtract the first x. So I could use this table. I'm just going to graph it. It'll make things easier. I'm going to go to Desmos and graph it and use the table that they have. -2x squared plus 4x plus 6. If you hit the little gear edit list, you can convert that to a table. And I'm just going to look at the x values -3 and -1. I don't care about the others, so I'll get rid of those other ones. These are my points. This is the x1, that's x2. This is y2, that's y1. So I'm going to substitute these values in there. Let me shrink this a little bit. So when we go to substitute, my second y is 0 minus my first y, which is a -24. My second x is a -1. I'm going to subtract my first x, which is a -3. So I am just using these 2 points, which this one was a -1, comma 0. And this point, according to the table, was a -3, -24. That's what the table tells me about those 2 points. So now we just simplify using our math. 0 minus a negative number goes positive. What's 0 plus 24? 24. And then minus a negative number again goes positive. What's -1 plus 3? 2. 24 divided by 2 is 12. So the average slope is 12 units. So even though it's a curve and the slope is changing, the average slope between those 2 points is it's going up 12 units for every 1 unit to the right. Now I'm going to use the same graph, but this time instead of finding the average slope between -3 and 1, in part B, I'm going to find the average slope between 2 and 5. So we were checking the average slope over here. Now we're going to do it on this side. So we're looking at the average slope between 2 and 5. So that's what we're going to try to find this time. So I'll go to my table, and all I'm going to change is make this be a 2 and this be a 5. And now I got my points. So again, the formula for this was y2, which is -24, minus y1, which is 6, divided by x2, which is 5, minus x1, which is 2. There's my slope. Let's simplify. Negative 24 minus 6 more. Negative 30. And then 5 minus 2. 3. So the slope of my secant line will be negative 10. So every 10 or every 1 unit to the right, it goes down 10 units. That would be my slope for the secant line. All right, I'd recommend you use that table to discover what the slope is on the interval -2, comma -1 for this function here. I'll give you a few moments to find that value. All right, let's take a look at numbers. Example 6 now. It says find the average speed. So this is really just a application of what we've been doing. Here it says the formula for the distance traveled by falling objects on the moon is d of t equals 2.7 t squared, where d of t is the distance in feet and t is the time in seconds. Find and interpret the average speed of an object, time at the interval from 1 to 2 seconds. So what's weird is one, gravity is different when you're referring to stuff on the moon, and so let's see if it says feet. So on Earth, it falls at 16 feet per second squared. That's where that question, that amount comes from. And negative refers to it's falling down. What's weird on this one is it does not list it as being a negative value, which I think it should. But either way, this makes the object look like it's rising over time, which it's falling. So honestly, it should be going that direction. And so I'm going to clear this one out so you can see this. And so we want to find out exactly how fast it's falling. And that's why, well, it's saying the average speed. So maybe since a speed can't be negative, typically we all use it this way, but I'm going to go to table here and we'll look at the values. We want to find after the falling between 1 and 2 seconds. So that's really what I want to see on my table, is just from 1 to 2 seconds. We want to find the secant line between these 2 points. This would be the average speed of falling. And so let's see here. The average speed of the object would be, you would use the secant line formula. And so I'll take my second value of 10.8. That's the distance it fell, and or where its position is now, minus the original, which is 2.7. And on the time, you'd have 2 minus 1. So what this is going to say is for every 1 second that the object has moved, for every 1 second, it has moved roughly 8.1 feet. And so the average speed here is that the object, object is falling 8.1 feet. I don't know why I did rounding. This object is falling 8.1 feet per second between 1 and 2 seconds. That's the speed at which this object is falling. And so that would be part A. Now part B, we want to do the same thing, but now we want to look between 2 and 3 seconds. So now between 2 and 3 seconds, let's just use the same formula again. The object would fall 24.3 feet minus the original distance it fell on, which was 10.8 feet. And again, we'd have a final time of 3 seconds minus the original time of 2 seconds. And so here, when I do my subtraction, I think I'm going to have 13.5 in the numerator over 1. So this would say that the object is falling 13.5 feet per second between the interval 2 and 3 seconds on that interval. So with that, I'll let you try this DOL. All right, let's take a look at this ACP release question. It says a soccer player kicks a ball at an angle. The height of the ball in feet varies with time and is given by this function, where t is in time in seconds. What is the maximum height of the soccer ball to the nearest foot? So if you're thinking about this one, what we would do is just type it in, and once you look at your point, I have a question for you. How would you get your correct answer? If you see maximum, you would go to the maximum. And now what would be your correct answer when you look at that? It says, what is the maximum height? Which variable is height? The T or the H? Because H is in the place of Y, you'd be looking at the Y. And it says round to the nearest foot. Answer would be 17. And you need to bubble that in. You do not have to put the plus, but you do have to put the 1 and 7 bubbled in. And that would be your answer for that one. All right, let's look at one more ACP question. This is graphing piecewise. And so I started at the beginning of the lesson with this, and I'll finish here. If you go to your Desmos pre-programmed graphs and you click on the piecewise calculator, which is the second calculator here, and you open up this link, you could graph this equation and determine which graph is correct. So the first branch here that says step 1, the first branch of this equation, which was just negative x minus 2, while x is less than or equal to negative 2. And so that would be this piece portion. The second piece of the graph is that we have a negative parentheses x squared, so it'll be upside down parabola, minus 4 between the x values of negative 2 and 3. And then finally, we'll have a third piece. So I want to open this one up. We'll have a third piece, which is just negative 6, as long as x is greater than 3. And so there's the third portion of the graph. Now, what's going to really help you with Desmos is it will show you a solid dot if there should be a solid dot. So when I look at this picture, I can quickly eliminate the top 2 graphs, A and C, because there's no gap between the second and third piece. There should be. And the Desmos tells me the bottom piece should have the solid dot. So B is the correct answer. Now, if you want to do this by algebra, this is telling you your range value given your domain. And I want you to see at when x is greater than or equal to 3, we have the point negative 6. So to walk you through it, here is 3. When x is equal to 3, it's going to equal negative 6 as a y. And so you notice that that's a negative 6. That's where that point came from. Whereas over here, the end of the second piece, it's less than 3, which is an open circle. And if you plugged in that 3 squared is 9, subtract 4, you get 5. Make it negative, we have a negative 5. Notice how this one's a 3, open circle, and negative 5 there on the y-axis. So that's how it works if you used algebra.